We are still talking about learning in the case where we sample from the environment instead of having access to the full, probability transition function for the environment. So in the Monte Carlo chapter, recall that we had done prediction directly by measuring G. And in this case, G is the discounted future return from time step T. And we get this by just actually having an episode, the full trajectory, and we can then calculate this for every state that was visited along the trajectory. Now, either way, we need this expected value of G. And in the case of Monte Carlo, we just use the sampled value. But an alternative is to use this other estimate for the expected value of G, which is based on an equation in the previous chapter where we looked at just the next reward and then the value estimate at the state we end up in. So, right, and this is from the definition of G because, right, like this sampled is equivalent to G. And in fact, if V is converged to the correct value function, then, this quantity, is the expected value of G if we take the expected value of this. And now here we're replacing the expected value with averaging up these samples. In this case, we're going back to using a constant step size alpha. Remember that this was what was used for the non-stationary problem. So in general, this might be preferred for reinforcement learning. It's just, I guess it's a more flexible technique, but this alpha could be any sort of weighting term for doing an average. This is just the constant step size method of averaging. And this is also the incremental update rule, which we went over before. So like this is a way to calculate an average incrementally where we have the target here and we're taking the difference between the target value and the current value, and then we're using that to update the current value. Right? So we're still, we're not going back over all these other aspects of like why this calculates G and why this incremental update rule works. We already went over that before. But the end result is we do something very similar to the Monte Carlo process, except that we can actually perform these updates during an episode. And that's because the only thing needed to do the update is the information about the next step. Right? So here we can actually update during an episode rather than waiting until the very end of an episode, which is when we have the full, G value sample. So are there any questions about this, how this compares to the Monte Carlo or full Monte Carlo here? What we actually are still sampling sort of with Monte Carlo, but it's being combined with this sort of bootstrap value, meaning that we are using part of the value function itself to do the update rather than relying only on the samples. Actually, here is also a summary of the definition of the value function and why this works, showing how we could either just take the expectation of G or we could replace G with this. And remember that because the value estimate, the state value function, state S, is the expected value of G at whatever that time step is, we can actually calculate the expected value of GT using, the value function at the next state. Hence, the use of bootstrapping in this method. And from the backup diagram here, we could see that this sort of is cut off after a single step because all we need to finish the update is to get the value estimate at the next state. So is this any questions about this? The pseudocode or the why the method works in the first place? Well, I have I mean, you can implement this. Actually, this doesn't even really need to be a separate implementation, but here, like the information we need from the environment here is, we need to know what the states and the actions are because we're gonna ultimately tabulate by them. Or I mean, it's helpful to know what they are ahead of time. And then we do need a way to initialize the environment with a state. And we basically, instead of, I mean, we need this step function. And in this case, what the step function is going to do, and what when you define this, it's going to take a state action pair and it's going to return the transition, which is the reward and the next state that we end up in. Also, because this could be used for episodic or continuing tasks, it's helpful to know when you're in a terminal state. You could either do that by having a defined terminal state, or in this case, there's another function which then checks. You can always call it on a state, and it will tell you if that state is terminal or not. And then you know that the episode can end when the state is terminal. So, and then once you have this step function, then you can easily create a function that runs an episode from start to finish using the step function. And all it will do is take a step, get all of the transitions from the step, and then proceed until the state is terminal, at which point the episode will end. Of course, this function only makes sense in the case of an episodic task, because if it was a continuing task, you would never reach a terminal state and the episode would never end, hence the term continuing task. Then this quantity here, like this term in the brackets, is what is referred to for both methods as, this is sort of the update quantity. It's the thing we're incrementally adding to the value to update it. And in the case of the TD method, this is called the TD error, the temporal difference error for a single time step. The TD zero error, because it's the shortest TD method possible because it only uses a single step into the future. And what is shown here is how, if you have these two forms of the error, so for the Monte Carlo, we had this, and for TD, we have this. And they can actually be expressed in terms of one another. And you can see that here with this trick where they just, we actually end up writing this quantity by expanding out G, right? So we have, G of T can always be expressed as the reward plus the G at the next time step, right? And then we have this minus S of T. And then if we add and subtract the value at the next time step times gamma, which is the discount rate, then we can rearrange the terms, noticing that these terms form delta, or actually, yeah, if we collect some of these terms together like these, we get delta, and then what we have left is the original expression here. So now this whole expression can now be, like, we can take this entire right-hand side, and replace it inside of here. And this can proceed iteratively until we get to the terminal state. Right, so like, since, if you notice, like, we have this expression here on this step, right? Like, because the term in the parentheses here is exactly the same as this left-hand side term advanced by one time step, then this derivation can just proceed out to infinity by just, incrementing this and applying this recursive rule over and over again. And at the end, these quantities are all zero because at the terminal state, the return and the value estimate are both zero. So this ends up forming a chain of these TD estimates. And we can see how the Monte Carlo update is just the equivalent of all of the TD error updates, but added up until the end of the episode, discounted by the appropriate, power of gamma. So the methods, do line up onto each other. Like if you had gone to the end of an episode, accumulated all the TD, error updates, then that would end up matching the Monte Carlo error. But the TD updates occur, during an episode is the difference. So is this any questions about this derivation? Or the relationship between the two methods? Because, okay, we can, I guess, discuss this first exercise. So the question is, this derivation relied on the fact that the value function doesn't change during an episode. So we like wait until the end of an episode and then perform all of these updates. Whereas like in the pseudocode, the reality is that we're doing these updates, during the episode, right? So like the next time we arrive at this state, like if we visit a state twice, then we're going to actually be doing an update based on the updated value function. So in this derivation, there's just this quantity v, right, where we just have these estimates and they don't change throughout an episode. But the question here is, what is the difference if the values do change during an episode? So now we have, the value function at time t, which are the value estimates we have at that time. And it's asking you to redo this derivation and what is the difference? And I mean, this question is pretty technical. Like the only real way to do it is to actually, write down the derivation and see what happens. But the result is like there actually is a difference in the relationship, but it's somewhat instructive, like what the difference is. We can go over it. So this is just the equations that have already been stated in the chapter. This is the TD error, but now I am writing down a subscript on V, which represents the value estimate at time t. And now the TD error at time t is based on the value function at time t. And if we go back to the value update, remember that we're updating the value. So when we update the value, we have the value at time t plus 1 expressed in terms of the value at time t and the TD error at time t. So we can then proceed in the same way as this derivation, where we expand this out. We do this trick where we add and subtract the value function at the next state. But of course, this is still the value function at time t, but for the state for state t plus 1. So now we get to this expression, and we have almost the same recursive relationship as we had originally. But like here, we could already just proceed. But the problem here is, notice that this term in the brackets is not this term advanced by 1 time step, because that would mean that the subscript here would be t plus 1 rather than t. So there's a bit of a problem in that we can't, expand this recursively from this point. So we're going to do another trick, which is we're going to add and subtract the thing we actually want, which is v at t plus 1 time of this same thing. So like we would like this subscript here to be t plus 1, but it's not. So I'm going to define a new quantity here, which is defined as the difference in the value function at the t plus 1 state, but the difference in the estimate between time step t and t plus 1. Okay, so now I can rewrite this equation using this, this quantity eta, and I can do this. And now, because I've removed the terms out and put them into eta, now this term in the brackets actually can be expanded recursively because we have the thing we wanted, which matches the left-hand side, right? So now we do the same expansion here, but we have these extra eta terms left over. When we do this, we do the same thing expanding out to the terminal state. And then we end up with an expression that looks very similar to this, but there is this gamma eta term added to the delta. Now, if you look at what eta is, it looks like it actually shouldn't, it should almost be 0, like most of the time. And, that's because at time step t, so like when we do the value function updates, the value function update at step t plus 1, right? So the value function at step t plus 1, the only state we modify is the state at t, right? Not t plus 1. So if the states change between time steps, then this difference will be 0 because the value function at state t plus 1 was not updated, only at t. So it will be 0 if they're the same. If the states if the states are not the same, then this will be 0. And then in the case where the states are the same, then the quantity is not 0, and it's actually this value. It's alpha times delta t, because that is the degree of the update for the value function, right? So this is how much the value function at the state changes if the state stays exactly the same on the transition. So we can rewrite eta in terms of this indicator function that is only non-zero if the states are the same, in which case the update is the step size times the TD error at step t. So, this equation is actually the same as this, where I'm just replacing eta with this relationship. And notice that it is exactly the same as this formula, aside from the fact that when you visit a state twice in a row, there is this difference in the relationship. But otherwise, if the states are not visited twice in a row, then this term is never non-zero. So then it would be exactly equivalent to the case of not updating the value function during an episode. So it's just something to keep in mind, is that sort of all the assumptions and approximations made that assume no updates during an episode, if you do update during an episode, it does cause differences. But those differences only occur when you have the same state twice in a row, which there's plenty of environments where that would never happen, but it can definitely happen. We'll see, like in some grid world examples, if you hit a wall or something, you could end up in the same state after one step. So is that any questions about this derivation? Okay, well, we can move on to sort of the first real concrete example for TD learning. So in this example, someone is trying to predict how long it will take for them to arrive at their home. And there's different states, which are sort of points along the journey. And at each state, there is a predicted time to go from that state. And actually, a predicted total time because you have the elapsed time as well. So in this example, the prediction can change based on like something in the environment. So in this case, there's sort of a typical time that each leg of the journey takes. And if everything occurs as expected, then the journey will take 30 minutes. But, in this example, it takes 5 minutes to reach the car. And then normally it would take 25, or sorry, normally then it would take an additional 25 minutes to get home from reaching the car. But because it's raining, the prediction has gone up by 10 minutes, right? To 40. And then we exit the highway. But the journey on the highway apparently took 5 minutes faster than expected. So now the predicted time is actually lower. And then at this point, we're behind a truck, which now the prediction goes up by 5 minutes again because there's a 5-minute delay from the truck. And then in reality, the delay from the truck was a little longer than expected. So then when we exit, now, our prediction is now updated to this 43 minutes. So there's just a series of these updates. And the question is, how would you then go about updating your estimates for the future based on this data? So, and in this example, our value function is just, based on each state we're in, each leg of the journey. So apparently, we don't actually have access to this, like other information about like the fact that it's raining is not part of the state representation. Because if it was, we'd have like an entirely different estimate for the case of when it's raining. So here, we have our original predictions, and then we have the fact that, especially from the initial prediction of 30 minutes, our actual journey took 43 minutes. And if we did a Monte Carlo method, right, we would have this G, right? G here, this is like an undiscounted task. So the thing that we're trying to match is the predicted total time, right? That's like the objective we're trying to predict at every state. So in the Monte Carlo method, we would just end up correcting every value towards this predicted total time, which in this case, right, every state should have predicted that it would take 43 minutes. Now, the difference in the TD learning is that the prediction is now based on the next value estimate, right? Rather than being based on the final outcome of the episode. And here, at the end of each leg of the journey, we have a new prediction, which is partly based on how much time has elapsed previously, right? So when we get here, we have an updated prediction, which is 40 minutes because it took well, actually, I guess this part of the journey took the same amount of time. I'm not sure, but yeah, like each of these updates now is actually towards the prediction at the next state rather than towards the actual outcome. So we don't like shift every estimate fully towards the outcome. And if this kept happening, right, because this estimate's going to go up. So now the next time we do this update, this estimate's going to be up here. And then this estimate will get shifted up here. So like if we kept doing this with the TD update and we kept having the same outcomes, eventually these changes would propagate back and all these things would be updated to the actual outcome, but it will take like multiple steps to do that. And in the Monte Carlo method, that actual outcome immediately updates, you know, all of the estimates right away. But if we're just looking at a single step in the update, right, this information at the actual outcome doesn't propagate back through all of the states, right? Because the starting state will only receive an update based on the estimate at the next state, not on the information all the way out here, right? So until this information has time to propagate back through like multiple updates, you only get the information from a single time step. And that is sort of the main difference, which should be obvious from this update rule, where you see like the only information at state t we have access to is the step t plus 1. And that's sort of what's being shown in this diagram is, you know, the red arrows only represent information one step into the future, not all the way into the future. So does that line up with like people understand how the TD updates work compared to the Monte Carlo update? Because the next question is sort of, I mean, it sort of tests your understanding of what are the advantages and disadvantages of the TD method. And it sort of relates to how much information can pass back to the earlier states. So for this question about the driving home example, the question is, can you imagine a scenario in which a TD update would be better on average than a Monte Carlo update? Give an example scenario, a description of past experience in a current state in which you would expect the TD update to be better. And there is a hint here, which is suppose you have a lot of experience driving home from work, then you move to a new building and a new parking lot, but you still enter the highway at the same place. Now you are starting to learn predictions for the new building. Can you see why TD updates are likely to be much better, at least initially, in this case? Might the same sort of thing happen in the original scenario? So,
Well, it seems like, for the difference between the state and between the Monte Carlo and the TD0 prediction, given that in the second one, the state can be updated immediately at each step, which gives a more relevant estimation compared to the Monte Carlo one, where it has to run through the entire episode before it can update anything.
well, yeah, that's true. But even in the TD method, like these black dots represent the predictions for that episode. And in the TD method, we can update our prediction from reaching the car when we get to the next state, but we actually have to wait until we reach the next state to do this update. But then by the time we reach the next state, we have a new prediction anyway. So yeah, like you can update during the episode, but here the question is more about the value of these updates the next time we make the journey home. Because in both methods, we can't really, we're not like making decisions, like we can't actually improve our predictions, along the way. Because either way, we have to wait until we get to the next state to have a new prediction. So yes, TD you update during an episode, but considering all these updates that occur, and then you're considering, now we have a new set of predictions for the next drive. and they're different, right? For the Monte Carlo method, at least this is for an alpha of 1, or like this is for completely replacing the old value. We would then predict a 43-minute journey from every state, because that's the last length it took. Whereas for the TD0 prediction, we would have a different, updated estimate for each leg of the journey. So like from the starting point, we would actually only predict a 40-minute journey, even though the actual journey was 43 minutes. I mean, so this is the original scenario, but in the question, they're considering this sort of new case where suppose, we have this table of predictions. So this sort of represents our knowledge of the environment, predicted time to go, right? We add this to the elapsed time to get the predicted total time. But yeah, like let's just say, these are these predicted time to goes, and then we end up moving offices, so now we're in a new parking lot. So the predicted time to go from the starting point is surely going to be different, because the time from leaving the office to reaching the car will be different from what we're used to, right? Like this leg of the journey now is going to be different, and we're going to have new information about the elapsed time. But let's say like all the other things are the same. Like the only thing that's changed is we have a new like walk like to the car, so it might take, the expected time to reach the car will be different, but then once we reach the car, the predicted time at every step after that will be unchanged. And in that scenario, you could compare the updates that we would have. So, in that scenario, I'm saying is when we start the journey, let's say we have a prediction of 30 minutes. And this assumes some like elapsed time to reach the car. But then it actually takes 5 minutes longer than expected to reach the car because we have moved locations. The car is now like parked in a different spot. So the journey, and let's just say like nothing else changes, like everything else goes as expected. So the journey takes 5 minutes longer. And because this occurred at like the next time step, actually in this case, the Monte Carlo update and the TD update will be identical, because this change is only affecting the estimate at the next state. So, okay. So like, but according to this scenario I've just created, these updates are exactly the same. And there's no difference between them. But, this is assuming that nothing changes like out here. Okay. But, in general, like in this original example, there's always like things that happen later on in the journey. Okay. So this difference here reflects an actual change. Like this leg of the journey is actually different and is like permanently different because there's been a change to the environment. But like, let's say that in addition to, this real change, now there's like another change here. So I've like created a scenario here where now after we reach the secondary road and we get to the home street, now there was a delay on this leg of the journey, right? So actually, normally it's a 35-minute, like it should have been a 35-minute journey, but there was a 2-minute delay at the end. So the journey actually took 37 minutes. Okay, but like this delay is something that was random. Like on a different day, maybe this is actually 2 minutes shorter. On this day, it happened to be 2 minutes longer. So now we do the Monte Carlo updates, and we're going to update everything based on the total time of 37 minutes. But the TD updates will be different. In the case of the TD updates, we're going to update the original estimate based on the next state, which had this 5-minute delay. And then, this state will get updated from this 2-minute delay. But this delay doesn't affect the earlier states. And remember that this 5-minute delay is now a change in the environment that we actually want to learn. Whereas this delay is just one of the random things that could happen, and maybe another day it doesn't happen. So this is the difference with the TD update and the Monte Carlo. In the Monte Carlo, we're using this final total transit time to update all the states, and this it only affects the state immediately before the delay. So, can anyone see why maybe the TD update, if we're making like a single update, why this update would be more useful than the Monte Carlo update?
Well, again, based on the information between the Monte Carlo and the TD zero, having an update for each state, well, for each step of the state seems to be more useful compared to the average.
What do you mean exactly?
Yeah. Yeah, I don't have anything really to add to that.
Okay, so I didn't understand what you meant.
Yeah. Well,
Seems like the original Monte Carlo has like one prediction, whereas the new one now has like 2 levels of prediction.
Yeah,
Is
I mean,
that
that's true in the original. Yeah, in the original scenario, that's also true, right? Like, we're basically have the total time is the only thing used, and here, yeah, we have a series of different updates. Yeah, so that's definitely true, but the question is more why whether this is true or not, of whether these updates is more relevant to the problem than these updates. And this is sort of a scenario in which we have a change that occurred, a real change that occurred at the start of the episode. And then we may or may not have other fluctuations that occur later on in the episode. But it's sort of based on the hint in the problem, but it's sort of constructed this example to be an example of the TD update being more useful. But the question is, like, why is it more useful in this case? And it relates to sort of information we want to use versus information that we, maybe want to reject or not, immediately use.
The only other point that I could think of is between the Monte Carlo, where you basically have to wait till the end of the episode, while for TD it would probably allow for convergence.
Okay, yeah. So for this example, that aspect of, like, that is an advantage of TD. You can update during an episode, but that's not relevant to the question here, because here we're thinking about, right, the next drive. So all we really care about is these are the updates that happen. Forget about when, like, by the time we make the next drive, we have these updates. That's all that's important. So why would one have an advantage over the other on, the next time we make the drive? Not, you know, in the middle of a drive. Because like in the middle of the drive where we can't really do anything. Like we have to wait till we see what happens the next step anyway.
Well, given that example between the leaving office, which had the actual change compared to the second road, it can pick up on the change of those two different states, I think.
Mm-hmm. Yes, there is a difference. Well, look, I'll just point out that the information that we would like to learn, like to have accurate estimates, would be this update here. So like we want to understand that now the journey will take 5 minutes longer. And we already have good estimates for the later states, right? That's sort of the scenario being created. So in the TD update, regardless of what happens later on, we are going to have this correct update from the start. Whereas in the case of Monte Carlo, this starting update will actually get polluted by information later on that may not be relevant. Because like this delay may not happen again. This delay may, you know, there could be the opposite of a delay on a future episode. And this will all average out in the end. And the point is that in the case of TD learning, regardless of what method you're using or what happens on in future drives, future updates, at least the next time we make the drive, we are going to estimate a 35-minute drive. And that is the correct estimate because we already have accurate estimates for these future parts of the journey. The fact that this delay happened here may or may not be relevant. If we see this delay over and over, like the next 100 times, then yeah, it'll propagate back and eventually affect us. But for right away, the initial updates, the TD method is actually doing this update, like the one we would like, assuming that we weren't confused by anything that happened later. But, you know, there is another side of this. And so this isn't like mentioned in the book, but let's say that the opposite happened. Let's say that our home moves to a different part of the neighborhood on the same street, or like let's say our home moves further down the street. Okay. So now when we get to the home street, it takes 2 minutes longer than before to arrive home. Okay. So in this case, this is the TD update. So we're going to update our estimate, you know, here at the home street, and none of these get updated. But for the Monte Carlo update, every estimate is going to go up by 2 minutes. And actually, like without even changing anything else, in this scenario, can you see why the Monte Carlo update is better, you know, in this case, where now there's been a change to the very end of the journey, not to the beginning of the journey. Because like I've said that like the home is moved, right? So the trip is going to take 2 minutes longer. Like that is the new scenario.
Yeah, I'm just trying to think about why that Monte Carlo propagation of all the states is more useful in this case, compared to the other ones.
Mm-hmm. Well, so in the original scenario, if nothing happens later on, the updates will be identical. I mean but yeah, in this case, the TD estimate will not update the earlier states, at least at first, right? Because we're bootstrapping from this value. So if a legitimate change occurs at the end of an episode, it's going to take a lot of TD updates for that change to get reflected on the earlier states. Whereas in the Monte Carlo method, everything's going to get updated immediately. And then if we have, you know, a scenario where there's, again, like other problems, like now, let's say there is a faster than expected trip to reach the car for some reason, but then we still have this change here at the end, you know, then for the Monte Carlo method, actually every state is still going to get updated according to, you know, the total time of the journey. Actually, why does this say? Oh wait, sorry. So like in this case, because there's like a 2-minute faster time here, and then the time home was 2 minutes slower, right? Actually now the total trip time is 30 minutes and it should be 32. So like all of these updates, you know, at least this 28-minute time, like that we predicted here, these updates are still going to move closer to the 32-minute time. Whereas in the case of TD, because all of these predictions are unchanged, you know, these intermediate states are actually going to have like an even faster estimate, like for now, until the end, because, and they're not going to get affected by this, you know, longer time to arrive home either. So it's just like all of the earlier states that aren't immediately, you know, preceding this longer trip time are not going to get information from that. So actually this is a more straightforward example of why the TD just being worse without even introducing like other random events happening. Right? Because you can see that like the reality is that our predicted time should be 32 minutes. But it's going to take a while to see that with this method. So you can create examples where, you know, either method has an advantage.
So it seems like basically the efficiency of propagating changes, you know, upward and, you know, forward and backwards, where TD does it better for tail end propagation, while it seems like Monte Carlo does it better for the earlier states propagations, and then reflecting on all the other states.
And really, I mean, TD is better at preserving more information throughout the states. So like here, it, you know, preserves like this estimate here because this noise doesn't happen until later. So whereas Monte Carlo will treat every new piece of information as relevant to the values, you know, regardless of how far in the future. So if you have an environment where, you know, states are more affected by things in their immediate vicinity, then TD is probably better or more efficient. Whereas, you know, if you have an environment where distant things like really have a large impact on the states, then Monte Carlo will give more immediate feedback in that scenario. Okay, well, it's just, this example is like worth, you know, thinking about and coming up with your own cases. But as we move on, there are lots of like, there is more to the discussion of the advantages of TD methods. More in terms of the stability or the accuracy of the estimates. And of course, one of the main advantages is that we can make value updates, you know, in the middle of an episode, which is very useful, especially if we're worried about the episode even terminating. Also, if we have continuing tasks that don't terminate, we can't use Monte Carlo methods because we're never going to have the sample value of G, right? If the episode doesn't actually terminate, because we have to calculate that future sum. So that's certainly a major advantage. But again, like it's not entirely straightforward which method is better, and there's certainly cases where Monte Carlo would have an advantage, like sort of what I just said. But let's move on, to this example, which tries to illustrate some ways in which maybe the Monte Carlo method has a disadvantage to the TD method. So this is a simplified example because there are no actions to worry about. This is just a Markov reward process where we start in the middle, and at every step we randomly move either to the right or the left with equal probability. And at the ends is a terminal state. And if we terminate to the right, we'll get a reward of 1. And if we terminate to the left, we get a reward of 0. Now, without proving anything, it should be kind of intuitively obvious to people that you have an equal probability of terminating to the right or the left after some number of steps. I mean, this whole problem is symmetrical. So you sort of, when you start an episode, have an equal shot of getting a reward of 1 or a reward of 0. And it should also make some sense that the closer we are to the right, the more likely we are to terminate to the right. Right? Because we're closer, we're starting closer, and the closer to the left, the more likely to terminate to the left. So does that sort of setup make sense to people? I have a little here. If you look at this little diagram here, so this is showing like an example episode. In this example, actually, it took 3 steps to the right. So that's good. But if you change the random walk, here it takes you to the left, and in general, this can go on for a lot of steps, right? It could sort of wobble back and forth, but here you could just see different examples of random walks. Like here, this is a 7-step walk that terminates to the left, and after bouncing around a little bit. So this is the problem setup. And the question is, what is the value estimate, or what should the value estimate be for each state? Now, this is calculated later, but I can tell you that with this example of having 5 states, the value estimates, or the true values for these states, are these fractions of 1/6, 2/6, 3/6, 4/6, and 5/6. And this also sort of reflects the probability of terminating to the right? Because the reward is 1. So it means that if you're in this state E, if you're already in the state E, then sort of 5/6 of the time you will exit this to the right. And if you're in state A, it's the same thing where 5/6 of the time you'll exit to the left, resulting in the expected reward of 1/6. Okay, so these are the true values. And then, we can look at actually using either TD0 or Monte Carlo estimation to try to estimate the state values from collecting data from these random walks. So we're going to just do, apply the pseudocode for both the previous chapter and this current chapter. We're going to run a bunch of episodes, in this case up to 100 episodes, with different, we have this sort of free parameter, the step size parameter we can pick. And the smaller the step size parameter, the slower the convergence. But here, these are the curves showing how close the value estimates are to the true values, which is represented by this black line, right? Those fractions. And what appears to be the case is that over a range of different possible parameters, the TD method seems to more quickly produce more accurate estimates. This is just one example, but this sort of holds actually. So in here, I can actually add more states, so I can change the problem. So now this is like a longer chain with 9 states. So the episodes take longer, but you could see that you see the same sort of thing. So the blue curves are the TD method. You could see that the TD method seems to have a much easier time reaching accurate estimates to the Monte Carlo method. I mean, they'll both eventually converge to the correct answer. It's just that this is converging faster. And that seems to be a property in some environments, that because the TD method is able to make use of the information of the surrounding states, it can converge more quickly. Even though I made an argument in a different type of scenario where it would be slow because maybe it takes a longer time for the information to propagate. In this case, this probably also has an advantage in that this reward of 1, if we do the Monte Carlo method, the feedback, like the error we get, is either 1 or 0 for every update. Like we're either going to terminate with 1 or 0. And those values are not, close to the true values, right? Like we actually need these fractional values. And in the case of the TD update, we don't fully use that reward. So that reward value of 1 here, let's look at the TD update. So this reward value of 1 is only going to exist, right, for the states right near the end of the chain. And near the end of the chain, those are also the closest values to either 1 or 0, right? Like state E is 5, 6, and 1, 6. So this R value, if we actually make the transition, we're going to get that feedback of 1. It's close. For every other state, there's no reward, right? Every step, the reward is 0, except for the terminal transition. So then we're going to make use of the bootstrap estimate of the surrounding states, and those values are going to be converging to the correct values. So actually, for all the states in the middle here, the TD update is going to be using a much more relevant correction than the Monte Carlo method, right, which is only going to use G. And in this case, G is either 0 or 1. So, right, there's like actually a higher variance on the update pieces to the Monte Carlo method in this particular example, right? Because remember, like the Monte Carlo method doesn't use anything about the surrounding states. It's only using G. Versus, the TD is allowed to bootstrap. And actually, that may be why, as I make the chain longer, this difference actually gets more pronounced, right? Because like there's more of these intermediate states that have value estimates that are far away from 0 and 1. Whereas if I make the chain, so this is sort of the opposite extreme. If the chain is length 3, now there's not much of a difference between the methods, because we only have, I mean, still like TD is actually still better because it's better at dealing with the middle state, because the middle state should have a value of 0.5 and these should be 0.75. But you can see that there's like less of a difference. Yeah. And this sort of scenario where there's intermediate states whose values are very different from like the value at the very edge of the problem is pretty common. So that's sort of, if you have a problem like that, that's one reason why TD methods could converge faster. So any questions about the random walk example? Or the whole point of it, which is arguing that, TD methods have an advantage in some cases?
let's see. Well, the sense of how, the estimated TD values makes sense given that, at least, for the random walk example, you can basically brute force calculate it by having the matrices, and then basically figure out the stable state of that matrix by multiplying it. I'm just trying to think about why the TD converges faster, which I presume it's because of the updates of the states at each step causes it to converge faster because each episodes has more updates.
No, I mean, each episode will have the same number of updates. I mean, every visited state will be updated once for every time it's visited in both methods. But what I was saying is that, well, actually, we can go back here I mean, this is what I was asking if this argument makes sense, but for the Monte Carlo updates, these are the updates. G is either 0 or 1, right? So even the middle states are going to get updated by this value of 0 or 1, which will average out to the correct value, but it's far away from the values in the middle here. Whereas in the TD update, this reward is completely ignored. I mean, it's always 0, except for the right termination. So most of the update is coming from the value estimate for the neighboring states, which is going to be converging to these fractions. So that's why the Monte Carlo updates have a higher variance than the TD updates, because, right, they're either 0 or 1.
So, similar to like, the previous example where it was basically noting that of how the nature of the Monte Carlo and the TD updates, where that propagation is from state to neighboring states for TD, while for Monte Carlo it's only from the end states that's being updated.
Yeah, and in this example, the final reward is actually not any of the value estimates, right? There is no state with a value of 0 or 1. So you could understand why the variance is higher, because, I mean, this is true of a lot of problems where the reward we end up getting, or even like the discounted sum of future rewards, is very far away from the value of that state. Any single sample is far away from the value. On average, they will equal it if we average them up, but it's a high variance estimator because each individual sample of G is far away. And of course, we eliminate a lot of that variance with the TD update because of the bootstrapping. So I think for me, that's the most straightforward explanation of why the TD updates are more efficient. But it depends on the problem, because there's problems where that is not the case, but it is the case in this problem. But this random walk example leads to other questions, which I think are pretty good at challenging the understanding of the random walk. So this first question is, from the results shown in the left graph, it appears that the first episode results in a change of only VA. What does this tell you about what happened on the first episode? Why was only the estimate for this one state changed? And remember, this is for here. This is for this figure here. So I guess one hint is that actually on my graph, which I could regenerate, it's the opposite. Only state E was updated after one episode. In the book, only state 1 is updated, right? This red line represents the updated values from the TD0 update after one episode. And on my chart, it's this green line here. So, or there's one episode where we updated the values from a single episode. So what does it mean? What happened in this episode that is the basis of the book figure, and then what happened, you know, in the episode simulated here, you know, in this notebook, because there's a different update, right? State E was updated.
Well, I presume because that propagation would only lead to one step at a time. Because the other neighboring, because if you look at the neighbors at the middle state, the two neighbors at the middle states, are the same values, and so there wouldn't be a change. While if you look at the one that's at state B, only A, there's the state A that changed as a neighbor, and then state C didn't change, and so it would only well, I
Yeah,
think
so
that
here, state A is updated. So what does it mean happened in this episode? It's after one episode, state A was updated. So it means you know what occurred during the first episode.
and then that means that during the first episode that it reached the left state initially.
Yeah. So an episode terminating like this, right, would result in only an update to state A based on the reward of 0. But in my chart, state E was the only one updated, which means that the first episode happened to terminate to the right, thus only changing this estimate. So is that these lines are showing the estimates approaching the correct value over, up to 100 episodes. But if you're doing TD learning on this environment, right, one episode will only end up updating a single state value here. And that should be obvious from the way the update rule works, right? At starting, all the values are the same. So there's no information other than the information from the terminal transition of either 0 or 1. So, I mean, the next question is, the specific results shown in the right graph here are dependent on the value of the step size parameter. Do you think the conclusions about which algorithm is better would be affected by a wider range of alpha values? Is there a different fixed value of alpha at which either algorithm would have performed significantly better than shown? Why or why not? So here, there's 3, or in Monte Carlo has 4 alpha values. TD has 3 alpha values. You can see how the curves change with alpha, but I'll remind you that the smaller the alpha, the slower the convergence. And then if alpha is too large, if alpha is large, you get fast convergence, but you won't necessarily converge to the correct value if alpha is too big, because the convergence is only guaranteed if the alpha decays to 0 over time. So there is a balance to be had here. We're looking at just constant alpha. The alpha is the same. And the larger the alpha, it could end up converging to a value, to higher error values. I mean, it'll, the estimates will actually fluctuate because of how large alpha is. They won't be completely stable. So you'll have some sort of error threshold that you reach, like here, where we can't, get below this error. But if alpha is small, we could, in theory, converge to a lower error, but the process is slower. So that's what you see in these different curves. And the question is, like, do you think TD only looks better than Monte Carlo because they chose specific values of alpha that make it look that way? Or is it actually true that it's better in general, based on what these figures look like? So any idea about that? Or believe the conclusion here, or think it's just sort of the result of selectively picking alpha. Or, I mean, if you don't, I can just, do you have any idea, or do you want?
No, I don't really have a hypothesis about how the update
Okay, okay.
for alpha.
Sure. So I told you that if alpha is smaller, it converges slower. That's the problem, but it could reach a lower error. For the TD method, the smallest alpha being plotted here is 0.05, but it actually has the lowest error. So like the only problem with the smaller alpha is slower convergence, but this is already converged to a lower error than the other twos. So I would say if alpha, it's possible that with an even smaller alpha, you would reach an even better TD error here, because what we haven't seen the range. Like if I lower alpha to 0.04, it's possible it will, within this time frame, converge to an even lower error. In the case of Monte Carlo, we have the largest alpha of 0.04 converges here. It's already kind of in the regime of being capped at how low the error can get. And then if we lower alpha to 0.01, it's actually converging so slow that it doesn't reach a low error compared to this. So whatever the optimal alpha is over the first 100 episodes is within this range of 0.01 to 0.04, because we've already hit the two extremes. We've already seen convergence that's too fast and is capped, and this convergence is too slow and isn't able to reach a lower error. So it seems like the performance of Monte Carlo, whatever alpha we pick, is going to be in this range here of this performance. Whereas TD, I mean, could actually be even better. Let's say this doesn't even show off, like you'd have to get an alpha of even lower than 0.05 to see. So say that.
So if there isn't, so since alpha isn't decaying at all, since that means that the dimensional space, it would basically start to bounce around a minimum point instead of going down to the actual point.
Mm-hmm. Yeah, because it doesn't, alpha isn't allowed to decay to 0. But yeah, so TD is definitely converging faster, even with, as we lower alpha, it has, so definitely over this time frame. But remember that if we went out to many episodes, like if we went out to thousands or millions of episodes, both methods, can be made to converge to the correct value. It's just more a question of how fast the convergence happens. Okay, question 6.5 is actually pretty interesting, but it's a little technical. We don't have to talk about it now. 6.6 finally is about actually calculating the true values, which were listed as these fractions. And the question is to describe ways in which they were computed and what would you guess was used. I mean, this is also a pretty good question for understanding, how to compute value estimates when you know everything about the environment. Here, like the environment's fully defined. We can, I mean, I might as well just explain the answer, I guess, and we can stop after that. But I think like this is a pretty good exercise for understanding like how the Bellman equations work, or the relationship between Monte Carlo and TD. But so for the two methods, one method is you could set up a system of equations, and the system of equations is representing the values in terms of their neighbors, which is exactly what the TD update does, which is the bootstrap method. So, right, the value of every state is basically equal to the probability of transitioning to each subsequent state times the value of that state. And in the case of state A and state E, we have the advantage of knowing that for one of the transitions, we actually know what the value is, which is, or what reward we get for that transition. Actually, wait, have I said this correctly? I'm sorry. It's the reward. It should be the reward of the transition plus the value of the state we end up in. So in the case of state A, we have two possible transitions. In one of the transitions, we have a reward of 0 plus the value of the terminal state, which is always 0. Or we have the value of state B. And those are going to be average because we have a 50% chance of each transition. And for state E, we have a similar thing, except we have the value of state D, and we have the value of this transition, which is the reward we get for going right, which is 1, plus the value of the terminal state, which is again 0. So from the system of equations, you can start simplifying things. We have, 1, 2, 3, 4. So we have 5 equations and 5 unknowns, and that means that we can, solve it. And here I'm just solving it with basic algebra, but you end up with a state value A of 1/6, and then that propagates out, and you can calculate the value of all the other states. Now, the second possible method is that you look at a given state and you try to directly calculate the probability of terminating to the right or to the left. So here I've shown the beginning of the calculation. And in this case, when we're adding these up, the only things we actually have to add are the terminations to the right, because those come with a value of 1, whereas the terminations to the left have a value of 0. So we just need to calculate all the different probabilities of, we need the total probability of exiting to the right from state A. And that requires calculating the probability of all these paths, which involve bouncing back and forth. So the most direct route is we go 1, 2, 3, 4, 5, and in 5 steps, we exit to the right. That would have a probability of 0.5 to the 5th. But then we also have the case where we hop back once, and then we add basically 2 steps to the journey. And then we have all these other cases of bouncing around in different ways, and it's very complicated, and it's not very straightforward how you would add all these up. Of course, we already know the probability is 1/6 from this earlier calculation. But this calculation sort of represents what you would do with a Monte Carlo method, which is you're in state A, and you actually start sampling this probability. And you sample how many times do we exit to the right versus how many times we exit to the left. Whereas in the TD method, we're making use of the relationship between the states. And I would say that this method of calculation is a lot easier and more straightforward. This one, I'm not even sure how to, finish the calculation. And in this example, it was also the case the TD method converges faster, which there's some sort of nice connection here between the fact that the TD method converges faster and the fact that it is a more direct and straightforward calculation to use the TD style equation to calculate this, rather than, the Monte Carlo method. It seems to require a lot of samples to actually get this probability accurately, which is reflected here by the method converging slower. So I guess next time we could go over 6.5 if people are interested. It's sort of an interesting question, which I think I have the answer to, but it's a little subtle, probably why it has an asterisk on it. And then we can, proceed with more of the chapter.